Welcome everyone and Happy New Year. Welcome to the fifth session of the Probabilistic Machine Learning Reading Group. And today our session will not be about a chapter of the book itself, but we'll have a special session given by Max Hurt, a postdoc scholar at the University of Waterloo in Canada. And he'll be talking about how to mix what we've talked about so far. So working together with MCMC and variational inference. Thank you, Max, and the floor is yours.
Thank you very much, Pablo. Yeah, so today I'm going to be covering just a quick introduction to VI and MCMC, and then we're going to have a look at combining the two methods. We're going to look at ways in which MCMC is used within VI, and then we're going to look at ways in which VI is used within MCMC, and we're going to see how these two things kind of play together. Okay, so first off, variational inference. So the way I like to think about variational inference is that it's optimization over the space of distributions. And usually that optimization problem is posed as a minimization problem of a distance between members of the variational family Q, which are just probability distributions, and some distribution that we're interested in that I'll be calling the target, and is denoted pi here. And then once we've found our approximating member of the variational class, the task is to approximate expectations with respect to the target using the optimizing member of the variational class. So maybe we know E of Q star F of X explicitly, or maybe we can very easily sample from Q star, and so we can approximate the expectation using Monte Carlo. Okay, but immediately there's a huge problem, and that's that the space of probability distributions isn't even close to being parameterizable with any kind of parameter that could fit on any computer that we might want to use. So instead, what we do is we find some parameterized family of, or we posit some parameterized family of distributions that exists as a subset of the whole family of probability distributions, and we optimize over the parameter that parameterizes that family that we've posited. And then we compute, or we infer, the expectation with respect to the optimizing member in the way that I've described before. Okay. So in general, because the parameterized family will be a strict subset of the entire set of probability distributions, the results of our variational inference methods are going to be biased. But often, members of the parameterized family will be quite nice. And this is almost kind of by construction. So we construct the parameterized family so that it's easy to optimize over. And so therefore, number one, we know it's parameterized, and number two, we know that we can optimize over it. And usually members of this family will be nice in some respects, such that like their properties, so their moments or their correlation structure or their tailoredness can just be read off. And also you might very easily be able to sample from them independently. And therefore, once we've found an optimizing member of our parameterized class, we might say that variational inference is fast, because we can either read off the properties of the member of the parameterized class, or we can sample from them IID. Okay, so how is the optimization done? Well, often the target distribution is just a Bayesian posterior, and Y is the data here. In that case, we can make the following decomposition between the KL of the variational approximation and the posterior, plus this term equals the logarithm of the probability of seeing the data, which we'll call the evidence. And consequently, you can see that as the term on the right-hand side increases, because we have an equality here, the KL between the variational approximation and the target must decrease. And so, in fact, lots of variational inference optimization is done by attempting to maximize this quantity here, which is just called the elbow. Okay. And it's the expectation with respect to the variational approximation of the logarithm of the ratio between the joint density between the parameter and the data divided by the density of the variational approximation. And one kind of useful way of looking at this elbow is to decompose it into two terms. Okay. The first term is just the expectation with respect to the variational distribution of the logarithm of the joint density. And maximizing this thing is kind of natural to the aims of variational inference. Although if we only had this term, we might be worried that members of the variational family in the optimization step would shrink down to Dirac deltas. And so therefore the elbow has this kind of regularizing term, which we'll call the entropy term, that serves as a kind of measure of the spread of the distribution Q of theta. And so simultaneously, we're maximizing over the logarithm of the joint distribution, but we're also regularizing by the entropy. Okay, good. Right, moving on. What's Markov chain Monte Carlo? So usually in the setting of MCMC or variational inference, pi, our target distribution, is such that it's going to be quite complicated. It's not normalized, and so we can't sample from it, or we don't know the normalizing constant, so therefore we can't sample from it independently. And so we can't easily access its properties. And therefore, what MCMC does is it forms a sequence of measures, mu of t, that kind of tend towards the target pi in some sense. In particular, these measures are represented by states that are sampled from them, which I'll call x of t. And the dependency between those states is Markovian. This dependency between the states is kind of what defines MCMC, but it also increases the variance of the estimators formed that are constructed using the states. So for instance, we're back in the regime of wanting to approximate expectations with respect to the target. And the way that we do this in MCMC is that we throw away the first T naught states in our Markov chain, and then we use the resulting T minus T naught states to form our estimator, as you can see on the right-hand side. And because we have a Markovian dependence between the states, these estimators are going to have increased variance compared to if we just had independent samples from the target distribution. And the upshot of this kind of Markovian dependence is not only that we have estimators of increased variance, but also this kind of vague understanding that MCMC is slow. And this is because it's inherently serial. So to get the final state in the Markov chain, we need the state before. And to get the state before, we need the state before that. And so therefore, there's no kind of obvious way of parallelizing this MCMC process. But the good thing is that it is asymptotically exact. So for instance, when people create their MCMC algorithms, they usually, the kind of like baseline theory that they will have about the MCMC algorithms are results of this type, just laws of large numbers for ergodic averages over the Markov chain. So we know that MCMC is asymptotically exact, but because it can't be parallelized, it's kind of inherently slow. Okay, now just a bit of notation to help things along. Now, a time homogeneous Markov chain can be defined by a Markov kernel K at X, which is just a probability distribution that says that if you're at a state X in your Markov chain, it's going to tell you where to go next. Now, for the purposes of our talk, it will be helpful to view K as an operator on the space of probability distributions. So for all mu in the space of probability distributions, we define the action of K leftwise on mu with the following formula. So if you're in set A according to mu of K, that means you've taken a sample from mu and then you move one step according to the Markov chain and you just look at the probability of being in that state A or in that set A, sorry. And so to sample from mu K, all you need to do is sample Y from mu and then move the Markov chain one step from the position Y to take our sample from mu K. And so therefore our sequence of approximating measures just takes this form. Mu naught, which is our initial distribution, post multiplied by K to the power of T. Okay, now there are some special distributions that the Markov chains are constructed to be invariant under the action of this operation. And if pi is such that it's invariant under the action of that of the operator k, then we'll call pi an invariant distribution of the Markov operator k. Good. So as I said just now, our MCMC algorithms are constructed such that pi is invariant under them. And usually what that means under that assumption and under some other assumptions on the Markov kernel K is that mu naught K to the T tends to pi in some sense. And in particular, we can make some kind of quantitative estimate of how fast mu naught K to the T converges to pi. So here we have this result. If pi is an invariant measure of k, then you know that the total variation distance between mu naught k to the t, so that's just the distribution of the tth state of the Markov chain, and the target distribution is going to be non-increasing in t. And so this leads us to our first kind of key insight that we're going to use to fit MCMC within VI, and that is that mu naught k to the t is guaranteed to be closer to pi than mu naught if pi is an invariant measure of k. And much of MCMC theory is actually the attempt to find conditions under which we can actually quantify how fast this distance goes down with t. So for instance, people want to find results that say, okay, the distance between the distribution of the t state of the Markov chain and the target decays at some rate r of t pre-multiplied by a constant depending on the initial distribution, possibly plus some bias term as well. Okay, yeah, and r of t is like the rate at which the distance decreases, and R and B depend on K and pi. And C naught depends on the initial distribution. And this leads us to our second key insight for fitting MCMC within VI, just that the efficiency of MCMC is very sensitive to its parameterization or its tuning and its initial distribution mu naught. Okay, good. So now let's try and put MCMC into variational inference. Okay, using key insight 1, we know that K will push a variational distribution Q closer to pi. And using key insight 2, we know that how close K pushes Q to pi will depend on Q and K. And so therefore, we can use variational methods to optimize over not only the Q space, but also the K space. Okay, good. Now let's look at some examples of people using these insights to put MCMC within variational inference. And the first paper that we'll look at is this Markov chain variational inference paper from Salomons, Kingma, and Welling from 2015. Okay, the main idea here is just to use the teeth state in an MCMC chain as the variational approximation. So our variational approximation here, Q of theta, is equal to just the distribution of the teeth states of the Markov chain. But immediately there's a problem. So you remember the elbow term decomposes into this expectation plus an entropy term. And the entropy term actually needed access to the density of the variational distribution. But the problem is when we push mu naught through k t times, or even just once, then usually the density becomes intractable or inaccessible or incalculable in some sense. And so the solution that the authors work out is kind of fairly mathematical, but it's kind of analogous to the way that the elbow, the initial elbow, like the original elbow, is constructed. So you notice that the original elbow is constructed like a constant minus a KL between some new distribution. So the new distribution is just the variational distribution and the target. And now the authors, in a similar way, define an auxiliary elbow, which is just the elbow minus here the expectation of a KL. And so therefore, in a similar way, we know that in the exact same way that we know that the elbow lower bounds the log evidence, we know that the auxiliary elbow lower bounds the elbow because it's the elbow minus an expected KL. And also, in a similar way to the original construction of the elbow, the authors introduced a new distribution that serves as one of the arguments of the KL. In particular, the KL is between this new variational distribution, and the maths works out that the KL is between that and the reverse Markov transition. And so to optimize this new quantity, the auxiliary elbow, we're simultaneously optimizing over our variational distribution. So we're optimizing over K, and we're also optimizing over the approximation to the reverse of the Markov transition. So we're doing this kind of like dual optimization. And we know that the elbow, the auxiliary elbow, lower bounds the elbow, which lower bounds the evidence. And so we know that the higher we get with the auxiliary elbow, we'll have higher lower bounds for the original elbow. Okay, and so we can sample reasonably easily from our Markov chain. So we can get unbiased estimates of the auxiliary elbow. And because we have routines that give us unbiased estimates of the auxiliary elbow, we can just use auto differentiation to differentiate those routines. And then we get unbiased estimates of the gradient of the auxiliary elbow. And in this case, because we've introduced a new variational distribution, the gradients are calculated with respect to both the variational approximation to the reverse Markov transition and also the parameters of the variational distribution, which are just the parameters of our Markov kernel K. And here you can see some plots that show contour plots of the variational approximation to the target, where we're varying a parameter of K from 0, 1, 2, all the way up to 7. And here is the plot of the exact contour of the contour, the contour plot of the target. And you can see that as you vary the parameter of K from 0 to 7, we'll get something that looks more and more like the target distribution. Okay, but the authors kind of run into another problem, which is that, okay, so in our MCMC talk, we were introduced to these chains that propose a point that they intend to move to, and then either accept that point with some probability or reject it with one minus that probability. And this accept reject mechanism is exactly the mechanism that means that K is going to be pi invariant, and so mu naught K to the T will tend to pi in some sense. But the problem with using these chains is that the auxiliary elbow will no longer be continuously differentiable. And so the solution that the authors use is just to Rao-Blackwellize the auxiliary elbow with respect to that parameter. So effectively, they'll take the expectation of the auxiliary elbow with respect to that parameter, But then we have another problem, just that the operation of Rao-Blackwellizing is exponentially expensive in the chain length. So taking these expectations and calculating them exactly with respect to the accept reject parameter, the longer the chain is, the the computation will get exponentially more expensive. And so therefore, in the case that we're using accept reject chains, we'll want to use very short chains within this framework. Okay. And so from all of this, we can kind of take some lessons. So lesson number one is just that the elbow is no longer calculable if we're using a Markov kernel within our variational approximation. Lesson number two is that using accept reject chains can cause discontinuity in the objective, even though accept reject chains are usually the ones that we'll want to use because they're the ones that ensure pi invariance. And according to the authors, apparently improving the properties of K reduces the variance of the gradient estimates. So that's quite an interesting point to note out there. Okay, next paper is amortized MCMC from Lee, Turner, and Liu. So as I said before, MCMC algorithms are constructed so that pi is the invariant distribution, and so that pi is a solution to the fixed point equation pi equals pi of k. Okay, and so approximating pi is the thing that we want to do in variational inference, and so therefore it can be done by approximating a solution to that fixed point equation. So we're just optimizing over the distance between the left-hand side and the right-hand side of the equation. Good. And they do this by just doing gradient descent on the parameter that they're optimizing over. But again, we run into exactly the same problem. If D is just the KL divergence, we need density evaluation of our variational approximation, which we don't have access to because we've introduced this Markov kernel. And so the way that they solve this is just to use a different D where we can we don't need to evaluate the density of Q theta K to the T. And also that gradients of that D can be estimated using Monte Carlo. And the kind of approach that they posit can kind of be viewed as fine-tuning a coarser variational approximation. So you'll have your K of theta, it's kind of coarse or bad in some way, and we apply K, which fine-tunes it, and we find our new Q of theta that attempts to look just like our original Q of theta with K applied to it. Okay, and here is an example from the paper where they're attempting to approximate this bimodal distribution. In the middle case, they use a multi-layer perceptron, and in the left-hand case, they have a very simple variational approximation that they then push forward through a Markov kernel. I think it's the metropolis adjusted Langevin algorithm, the kernel of that MCMC algorithm. And on the right-hand side, you can see the kernelized sign discrepancy between the variational distribution and the target. And so when you use fewer steps in the Markov chain, the discrepancy decreases very quickly at first. But when you use more steps in the Markov chain, you reach a better optimal point, but later on in the optimization trajectory. Okay. And so some takeaways that we can take from this is that, again, because we've introduced the Markov kernel, we have to reformulate or find a new objective. Another interesting thing is that the authors observe different dynamics for different T's, which is just shown in this plot, which I think is quite interesting. And from the fixed point equation, okay, from before, the fixed point equation just had T equals 1. But the authors use multiple values of T. So in theory, just using T equals 1 should be fine, but practically, so your K might be an accept reject kernel, and imagine that K is highly inefficient. So like you propose a point, and almost all the time that point gets rejected. In that case, Q of theta K is just going to look like Q of theta, because to sample from Q of theta K, You take a sample from Q of theta and you attempt to move it according to the Markov chain. But if the Markov chain always rejects the proposed sample, then you're always going to go back to your original sample from Q of theta. And so in that case, Q of theta k is just going to look very, very similar to Q of theta, even though Q of theta is not an actual solution to the fixed point equation. Okay, good. Finally, we move on to the third paper that I view as kind of a combination of the final two papers from Gallego and Rios Insua from 2021. So recall our variational approximation is mu naught k to the t. Now, in the first paper that we looked at, the authors optimize over the parameters of the Markov kernel k. In the second paper that we looked at, the authors optimize over the initial distribution mu naught. And in this paper, the authors optimize over both mu naught and the Markov kernel k. Okay, so they want to find the minimizing values of some loss between our variational distribution and the target distribution, where we're minimizing over both the parameters of the initial distribution and the parameters of the Markov kernel. And again, as always, the entropy term in the elbow is intractable. And so the authors kind of like construct many ingenious techniques to either approximate the elbow or adjust it slightly. Um, yeah. So check out the paper if you're interested in looking at that. Okay. Any questions so far?
I have one really quick one. You said the KL was not possible to compute because of you don't have the density, and because of that they resulted to kernelized sign discrepancy.
Okay. Yeah. So they didn't, I don't think they used the kernelized Stein discrepancy as the discrepancy. They have a couple of, they just use it to measure the distance between the variational approximation and the target here. But
But
I don't think they ever optimize over the KSD. They have various other divergences that they optimize with respect to, but I didn't describe any of them. Yeah.
and do you know the motivation for that choice, or
For this?
yeah, or any
Yeah,
insight?
I can guess. So it's a descriptive discrepancy. Like if the discrepancy goes to zero, then you know that your variational approximation will be equal to the
Mm,
target. Also, I know that to evaluate the kernelized Stein discrepancy, you don't need the normalized density of either the target or the variational distribution. So in that sense, it's like nice to work with, especially if the target is a Bayesian posterior.
mm,
And I think there's like a very straightforward way of calculating the KSD just from samples that you collect from your variational distribution. So that's my guess as to why they use it to measure like optimality in this case. But
mm.
yeah,
Okay.
but who knows for sure. Yeah.
Thanks.
Yeah. Okay. Any other questions? Okay. If not, we can go and talk about variational inference within MCMC. Okay. So as we saw from the latest paper, the parameters of the Markov kernel can be optimized over. And this idea has been around for a long time, and it's explored in the subjects of both preconditioning and adaptive MCMC within the field of MCMC. But unlike the case in variational inference, it's really not that easy to distill the efficiency of our Markov kernel down to like a single quantity like the elbow is in variational inference. But according to a kind of folklore understanding that I see coming from the sort of early noughties, properties, you kind of according to this understanding at least, you kind of want the properties of your Markov kernel to resemble the properties of the target distribution. So for instance, we might want the covariance structure of the Markov kernel to look like the covariance structure of the target according to this folklore understanding for all states X. Um, Otherwise, unless K has just a distribution as a tuning parameter, so like unless you can just plug in a distribution into K, it's not actually fully clear how to straightforwardly plug a variational inference method into MCMC. And I'll kind of elaborate on this point a bit more later because I think it's an important point. Um, okay, but in what cases can you actually plug in variational inference into MCMC? Well, the first case is nonlinear preconditioning via transport-based variational inference. Okay, so transport-based variational inference pushes a simple distribution nu through a diffeomorphism T of theta. And it does this to approximate the target distribution. So the variational problem looks like finding a parameterization of your push forward of a very simple distribution such that the push forward looks very similar to pi in terms of the KL. Okay. And so therefore, if nu is very easy to sample from, if it's sufficiently simple that it's very easy to sample from with MCMC techniques, and if this kind of variational inference program is successful, then we know that this KL will be small. And by the properties of the KL, we can just shift the diffeomorphism from this side to the other side after taking the inverse. And so we know that that KL will be low. And so therefore, the target pushed forward through the inverse diffeomorphism will now be easily sampleable because it's close to an easily sampleable distribution nu. Okay. And so therefore, we can kind of use this heuristic technique. So first, we find a parameterization of some good diffeomorphism theta star using variational inference. Then we can run an MCMC on the target, which is just the target pushed forward through the inverse of that diffeomorphism. And we know that the MCMC is going to run well if the VI works well, because then we know that pi pushed forward through T inverse is going to look like a very easily sampleable distribution. And so after running that MCMC chain, we'll have a chain whose states approximately are distributed according to this target. And so really we want states that are distributed according to pi. So to get those, we just apply T of theta to every single one of those states to undo the action of the inverse diffeomorphism. Okay, good. And the methods that are developed according to this kind of heuristic approach that I outlined on the previous slide fall kind of roughly into two categories. The first category is the category of measured transport. And if you want to check out work in this category, look at papers from Youssef Marzouk's group. Or it falls into the category of using normalizing flows. And so for that, you can look at papers from Mary-Lou Gabriel and various other people. Okay, and the distinguishing feature that distinguishes these two categories is just the form of the map T of theta. So in the measure transport case, the map has a very particular form, and it derives from something called the Knuth-Rosenblatt map, which is a particular map that is used in optimal transport. Unfortunately, we don't really have time to like go into exactly why they do this or what the map looks like. But if someone really wants to know, I can tell them at the end of the talk. And in the second category, of course, the diffeomorphisms look like normalizing flows. Okay, but because we want to do MCMC on pi pushed forward through T inverse, we need T to have particular properties. Okay, so we want T, it has to be invertible if the inverse exists, of course. But we also want to be able to evaluate the density of pi pushed forward through T inverse up to some normalizing constant. And so we want T to have some Jacobian whose determinant is easily calculable, so we can calculate that density. But equally, we want T of theta to be sufficiently expressive so that the variational inference program actually has a chance of working well. And these final two kind of things that we want of our diffeomorphism kind of fight against each other. So like the more expressive our diffeomorphism is, the less easy it will be to calculate the determinant of the Jacobian. Okay. The second kind of group of methods in which it's reasonably easy to fit variational inference into MCMC is something called adaptive MCMC. Okay, so MCMC kernels usually have tuning parameters, as we've seen before in the instances of papers in MCMC within variational inference. And good values of these parameters are often stated in terms of expectations with respect to either the target distribution or with respect to the Markov kernel. So for instance, if we just look at an example algorithm, the unadjusted Langevin algorithm with a matrix valued preconditioner L, which is going to be full rank, the Markov chain updates according to this equality. So you take your state x of t, you kind of shift it according to some generic scale sigma squared times LL transpose times the gradient of the logarithm of the target density. And having done that, you perturb the resulting state by some noise, which is shaped by your matrix valued preconditioner L. And so in that case, there exists various justifications for having LL transpose be either the covariance of the target distribution or for it to be the inverse of the covariance of the score of the target distribution. And so in both of these cases, our kind of optimal value for the tuning parameter L relies on expectations with respect to the target. And of course, because we're doing MCMC, we don't have access to these expectations. So the kind of idea is that we're going to infer them along the MCMC chain because the states in the MCMC chain are distributed approximately according to the target distribution. Okay. Or if these expectations are with respect to K, so we might want to maximize the expected acceptance probability of an accept reject method. And then in this case, the expectation is with respect to the proposal distribution. So if we're using an accept reject chain, so accept reject chains mean that you have your current point x of t minus 1, you propose a new point, and then you accept or reject according to some probability. If you're like rejecting all the time, that's bad. And so maybe we want to adjust the parameters of the Markov kernel such that we're not rejecting all the time. And this expectation is going to be with respect to the proposal distribution, which we know we can calculate because we're doing an accept reject chain. And so we have easy access to samples from the proposal. And so we can calculate these expectations quite easily. Okay, good. So as I said before, the key idea is that since we get approximate samples from pi and exact samples from the proposal, we can optimize as the chain runs. So here is quite a simple example where we're attempting to sample from a target distribution whose mass is kind of concentrated in an incredibly thin region here. And the top case is just a Markov chain where I've given it the kind of vanilla like default value of its tuning parameters. And in this case, and I don't allow it to learn from itself. So I don't allow it to learn as the Markov chain goes along. And so as you can see, the Markov chain doesn't really move that much. And so it only explores a very, very small region of the target distribution. Okay, and in the second case, what happens is that at each new at each new state in the Markov chain, you have some information about the shape of the target distribution. And so for each new state in the Markov chain, you kind of update your notion of the shape of the target distribution in the form of a covariance matrix. And with each new estimate of the covariance matrix, you use that in as a tuning parameter in the kernel. And this kind of dynamics has like a virtuous cycle style effect going on because if your states of your Markov chain are higher quality, then you get more information as to the target distribution from those states. And so therefore your estimate, the notion of the shape of the target distribution is going to be more accurate in these sigma parameters. And therefore your Markov kernel is going to be more efficient. And therefore the states are going to look closer to the target distribution. So you have this kind of virtuous cycle where you have better states according to the Markov chain, meaning better tuning parameters, which mean better states. So that this cycle kind of improves itself in this way. And you can see from the example just that okay, so this is the Markov chain, the dots at the bottom here. We start off not really exploring anything. And then as soon as we like begin to explore the target distribution, we have a kind of like a phase transition or like a cutoff effect where we begin very quickly to explore kind of like a large amount of the target mass, which you can see in the scatter plot on the right-hand side. Okay, so now we want to fuse variational inference into MCMC. So how are we going to do this? Well, we're optimizing over this parameter sigma 1 or any parameter of the Markov chain. The way that we can use VI is just to use variational inference methods to do this optimization step. Okay, so the first example I'm going to give of this is gradient-based adaptive MCMC from Tizias and Della Portas in 2019. Okay, so in their case, we have K be an accept reject kernel with a proposal Q of theta, where theta is just our tuning parameter that we're going to attempt to optimize over. And they define what's called a speed measure, which is just the expectation with respect to the proposal distribution of the acceptance probability times by e to the beta times the entropy of the proposal distribution. So if we only had this term, if we only wanted to tune the proposal to maximize the acceptance probability, the proposal would shrink and shrink and shrink and shrink until Q of theta was like a Dirac delta around X. And in that case, X and Y would be the same. And so the acceptance probability would always be 1, which is maximal. And so they need to regularize by the entropy of the proposal distribution. Okay, and they derive a lower bound on the logarithm of the thing that they're attempting to maximize with respect to the parameter theta, and that's this. It's the expectation with respect to the proposal of the logarithm of the acceptance probability plus an entropy regularization. And then they maximize this lower bound at each step of the Markov chain using a one sample Monte Carlo estimator. So they get at each step, you're guaranteed to get one sample from the proposal. And so you have a one state Monte Carlo estimator of this lower bound on the log of the speed measure. And we can note the kind of similarity with the elbow in this case, right? So before you recall that the elbow is like the expectation of something that you want to maximize plus an entropy regularization. And here it's again an expectation of something that you're attempting to regularize. Sorry, the expectation of something that you're trying to maximize plus entropy regularization. Okay, good. The next example of attempting to kind of put variational inference within MCMC is independent metropolis Hastings with normalizing flows. Don't worry if you don't know what independent metropolis Hastings is. And this is from Brofos and Mary Lou Gabriel and co-authors from 2022. Okay, so now we're in the kind of normalizing flow regime. And so we let T of theta be a normalizing flow and nu be a simple distribution. And the authors want to maximize the expected probability under the target now of the log density of the push forward through the simple distribution through the normalizing flow, which we can see as like a variational distribution. And now we can see this is exactly the same as wanting to minimize the KL between pi and the variational distribution. But note, in this case, it's not the reverse KL. So in variational inference, most often you're going to see the reverse KL being optimized over. And that's simply because we can't estimate the forward KL because it's an expectation with respect to the target. But in this case, because we're doing MCMC, we have approximate samples according to the target. And in this case, we can actually optimize over the forward KL and not the reverse KL. Okay. And then our variational distribution, which is just the simple distribution pushed forward through the normalizing flow, is used as like a proposal distribution in an independent Metropolis Hastings kernel. As I said before, don't worry about if you don't know what an independent Metropolis Hastings kernel looks like. Okay, so for each new state, x of t in the Markov chain, this state is going to be sampled approximately from pi. And so then you can do the ascent step where you take your parameter value theta and you perturb it by the gradient of the thing within the expectation that you're attempting to maximize. And because x of t is sampled approximately according to pi, this gradient kind of looks like an unbiased or probably biased version of a gradient of this expectation. Okay, good. And as I said before, since we get approximate samples from pi, we can minimize with respect to the forward KL now. All right. Now, what do I see? I was saying before, like there's not really an obvious way of putting variational inference into MCMC. And here I'll kind of explain why exactly I think that is the case. Okay. So the final example that I showed you illustrates what I see is a fundamental difficulty when trying to use variational inference within MCMC. And that's that an MCMC kernel and its components, so like its proposal distribution, is fundamentally a local object. It says, given a state in the Markov chain, local to that state, how are you going to move? So it's the MCMC kernel is always stated with respect to an initial state, and therefore it's always kind of like locally informed and not globally informed. Whereas a variational distribution is fundamentally a global object. It attempts to capture global properties of the target distribution. So it attempts to capture the correlation structure, or it attempts to capture the tailoredness, or it attempts to capture the moments. In each of these cases, these are global properties of the target distribution that the variational distribution is attempting to capture. Therefore, either we have to find Monte Carlo methods that have some kind of like globality to them. So for instance, I'm thinking about things like the rejection sampler, where you have some proposal distribution, right, that doesn't depend on a previous state in the Markov chain. It's just a distribution. And you want that distribution to look like the target distribution. And so rejection sampling is kind of global, right? Or an importance sampler, which is effectively the same thing, or the independence Metropolis Hastings sampler. So in each one of these cases, they do in fact have a global like a sense of attempting to capture the target in a global way. But note that the first and the second examples are not actually Markovian methods. They're Monte Carlo methods. And because of the fact that these methods are attempting to capture global information about the target, that they can fail catastrophically. In the case that the proposal distribution like misses the tailoredness of the target or misses the correlation structure of the target, these methods are known to just completely fail. They result in estimators whose variance is like incredibly high. Okay. Or you have to work out some kind of clever solution. You have to work out some clever way of reconciling the globalness of the results of doing a variational inference and the localness of a Markov kernel. Okay. So to kind of illustrate this point, I have like a simple example where we're attempting to sample from this pink. So we're attempting to sample from a target who, let's say, the target mass is concentrated within this pink ring. And let's say we're in the case we've like for some insane accident, we've done our variational inference and we know exactly the shape of the target distribution. So we're going to use it as the kind of like the shape of the proposal in a Markov chain method, in like an accept reject Markov chain method, right? And let's say we're starting from a point at this blue cross. So that's our current state in the Markov chain. Because we know the exact form of the target distribution. And because, let's say, we're using this folkloric understanding where the shape of the Markov chain proposal should look exactly like the shape of the target distribution, we have that the proposal is then going to be concentrated in the green ring, right? But if we propose points in this green ring, most of the points are going to be rejected. So in this case, this kind of folkloric understanding of the tuning of a Markov kernel within an MCMC method just completely breaks down. And the reason why it breaks down is the fact that like we've used the results of a global method, so variational inference, and we basically just like jammed them into a local method, which is MCMC. Okay. Good. Now, to summarize, if we're thinking about doing MCMC within VI, our thinking kind of is built from the fundamental fact that if pi is an invariant distribution under the action of k, then qk transpose is closer to pi than q. Okay. But immediately we run into the problem that the density of not qk transpose, qk to the power of t. We immediately run into the problem that the density of qk to the t is incalculable. So either we need to find a new objective other than the elbow, or we need to like do some kind of clever adjustments or a way of approximating the elbow. Okay. Secondly, we probably want to use an accept reject chain, because accept reject chains are usually the ones where we know that pi is an invariant distribution of k. So they're an attractive prospect, but they come with immediate drawbacks, i.e., like your objective is no longer continuously differentiable, or you need to marginalize out over the parameters of the accept reject step, which is going to be computationally expensive. And then we also kind of saw from the first paper that the optimization process depends on how efficient the Markov kernel K is. Okay. Now, if we want to take our variational inference method and do it within an MCMC method, we have the following kind of like lessons. So transport-based variational inference can be quite easily fit within an MCMC framework. So if you have an instance in which transport-based variational inference, you know it works really, really well, but you want an exact method, then you can fairly easily use these papers from like Mary-Lou Gabriel or from Youssef Marzouk to just jam your variational inference method into MCMC. Otherwise, according to the argument that I laid out on the past few slides, it's like very difficult or it's like not immediately obvious how to straightforwardly apply variational inference to the Markov chain Monte Carlo setting. And it's because of this kind of conflict between the locality of the Markov kernel and then the global nature of the variational approximation. Okay, and that's the talk. Thank you very much for listening. And are there any questions?
Thank you so much, Max. Are there any questions? If not, I can get started. So in this second part, about how using like combining both methods lets you optimize the forward KL. But
Yeah.
and that was when working with normalizing flows. And my question is that if we are already working with normalizing flows, which should be flexible enough that we can get a good approximation of the actual posterior we want to approximate, then shouldn't both directions of the KL lead to the same result?
Yes, if there's zero. So
Yeah.
if you can optimize like very, very low, then yes. Otherwise, you risk like this kind of mode collapse phenomenon
Yeah, yeah, yeah,
over
yeah, yeah.
scale, right? Yeah, yeah, yeah. But you're right. If you're able to like optimize really, really well, then yeah, then you're right. I think the thing is, in this paper, oops, what happened there? So yeah, in this paper, it's kind of not assumed that you can just like train the normalizing flow first and then just put it into the MCMC method. We're kind of assuming this like virtuous cycle dynamics. So you have like an okay normalizing flow, and therefore your MCMC method is going to be a bit better. And so the states that result from the MCMC method are going to be a bit better. And so therefore you do another step of your like variational inference optimization routine to make the normalizing flow better. So it's not the case where like you can do VI really well and then you put it in MCMC. It's like you can do VI kind of well and you can do MCMC kind of well, and you use them both together to do this kind of like virtuous cycle style thing. Yeah.
Okay. Okay, I have one more question that is just from a user's perspective, when would you use what? When
When
would you just resort to plain VI, plain MCMC, and when would you combine these methods in
yeah.
terms of both complexity, dimensionality, time, computation?
Yeah, yeah, yeah. Good question. So I guess it ultimately depends on like your end goal. If you have like a practical end goal where the states that you get or the approximation are used in like a broader routine where you don't need it to be exact, you just need a good approximation, and like maybe your variational distribution is being used in a wider setting, then doing variational inference can be very good because it's very fast and it gets you kind of like a coarse approximation of the thing that you want. But if your ultimate aim is to infer things and it really makes a difference, like the accuracy of your inference really makes a difference, then you're probably better off using an exact method like MCMC. There are cases in which both are just bad. So for instance, like if the target distribution is like has like concentration on a low dimensional manifold, and that manifold has like some insane structure and it has some kind of multi-scale thing where, you know, the variance of the target in one place is incredibly low, but the variance of the target in one area of the state space is incredibly high, then you might have trouble with either methods. Yeah.
Thank you so much. If there isn't any other question, I think we can conclude the session. Thank you so much for mixing these two very interesting topics, and we'll see you next week.
Yeah. Thanks for having me.
Thank you.
Thank you, Max.
Thanks.
Thanks.